So, hello Vaibhavi.
Hello, ma'am.
We will wait for 2 more minutes and then we will start.
Wonderful. Not an issue.
Okay. So welcome everyone. Welcome to the last problem solving session of this course, waste to energy conversion. So as usual, we will start by first discussing the slides. I will give you a brief recap of what was in week 8, and then we will move to the last year question numeric assignment of week 8, followed by one more numerical. So I'll start with this one. So the first module of week 8 was on numericals or problems based on esterification. Then we have the second module on cultivation of algal biomass and treatment of wastewater. So the contents of the this module is why algal cultivation? Why do we need to do algal cultivation for energy production? Next is algal metabolism and synthesis of fat and protein. Then classification of algae, lipid content in algal cell, algal lipids, and bio oil quality. Next, we will discuss conditions influencing algal lipid quality and quantity. What is the enhanced lipid accumulation techniques? Next is cultivation or growth of microalgae as an important step for algae to oil. These are the points we will discuss in this slide. So first is why algal biomass? So, as we know, algae are photosynthetic aquatic organisms. They can make their own food. So, for algae, inorganic carbon source CO2 is required along with water and light to produce food. Since algae is consuming inorganic source of carbon, so first what photosynthetic organisms do is they convert the inorganic source to organic source of carbon, and then they consume that organic source of carbon for energy and for biomass production. So algae is also very important in treating wastewater because for the growth of algae, nutrients are required, and algae can be very good for removal of nutrients from the wastewater. So microalgae are source of protein, lipid, vitamins, carotenoids. There are some pigments which are used in cosmetic industries. They are source of carbohydrate. So algae has wide application. It can be used in health industry, in food industry, for feed additives, for cosmetics, and for energy production. So the advantage of bioalgae and why we need to use bioalgae for energy production is following that it has very rapid growth. The algae does not require lots of controlling conditions. If we are applying the optimum temperature, what is the dose of nutrients required, then algae can grow very rapidly. And algae are very diverse. It can grow in fresh water as well as it can grow in oceans and saline water. So, and also some of the species of algae have very high yield of lipid, and these lipid are used for production of bio oil. Next, use all nutrients and minimize eutrophication. We know that because of discharge of high amount of nutrients, nitrogen and phosphorus in the river system or in water system by humans, there is a very huge problem of eutrophication in our rivers, lakes, and even in ocean. And these algae are a very good source to consume that nutrients and decrease the content of nutrients and prevent the eutrophication. Next is requires CO2 for growth, since as we know carbon dioxide is a greenhouse gas, and if it is using CO2 for its growth, then it is carbon neutral. It will not release any carbon dioxide. Next is it can be used as a fodder, and it can also be used it can also be used as a fodder for animals, and can also be used as manures for agriculture use. Next, algae are very diverse in nature. They have large, diverse species. They are microscopic to giant kelp, and their composition is also varied. So, algae are untapped source for high potential. It can be used for large applications. As we know, it can be used in cosmetics. It can be used in wastewater treatment. It can be used for energy production, and so on. Next is Algal metabolism and synthesis of fat and protein. So as we know, algals are autotrophic, so they use the phenomenon of photosynthesis to produce food. So during photosynthesis, what happens? Inorganic carbon along with water and photons, which are taken from the sunlight, then using this mechanism, some source of carbohydrate, organic carbohydrate, this glucose is formed along with oxygen. And this glucose is further used or organic carbon is used for production of lipid. So, and the lipid content in algae contributes to the production of biooil. Next, this is the metabolic pathway of algae for production of lipids. So, in chloroplast, what happens? Photosynthesis takes place, and three carbon sugar phosphate is produced, and this three carbon phosphate can either go and produce lipid bodies, or it can go and produce sugar. And there are also many other mechanisms through which this three carbon sugar goes and it produces lipid and sugars. Next is this is also the mechanism or simplified view for lipid synthesis in microalgae. Next, we have classification of microalgae phyla. So, in various phylum, microalgae are classified. So, first is green algae or chlorophyta. So, these algae have green chloroplast that contains chlorophyll A and B, and xanthophyle are accessory pigment along with chlorophyll. So they have mitochondria and they can have flagella. Flagella helps in movement of the algae. Next is red algae or rhodophyta. They have chloroplast with chlorophyll A and D, and phycobilins. They have double cell wall but do not have centrioles and flagella. Next is cyanobacteria or blue-green algae. Basically, these are not algae. They are prokaryotic bacteria, but they can produce their own food. They are autotrophic. That's why they are also called blue-green algae. So their chloroplast normally have chlorophyll A. They are not, they are bacteria, and they can work like algae to due to production of their own food because photosynthesis takes place. And some of the strains of this bacteria can grow in soil or marine or freshwater. Next, we have other phylums like eustigmatophytes. These are a class of eukaryotic algae which contains yellow-green chloroplast. So they can, some of the strains can grow in marine, freshwater or solid medium such as soil. So these algae contain chloroplast containing chlorophyll A. Next is brown algae. They contain chlorophyll A and C, and their accessory pigments are xanthophytes and carotenoids. Next is diatoms. These are they have chloroplast containing chlorophyll A and C. They have hard shell or hard wall due to presence of silica, and most of these can be found in fresh or salted water.
Hello, ma'am. Sorry to disturb you.
Yeah.
Ma'am, I wanted to ask, like, all these terms and the function of these algae, do we have to remember them for the final exam, or how is it?
I don't think that questions will be asked from these because these are basically biological parts, and we are
Correct.
dealing with the energy conversion. So it's just for your knowledge about what are the phylums on which algae are classified.
Understood.
But it's better
So,
to
ma'am,
once go through these and just have the knowledge about the different phylums or species of the algae.
okay. Thank you.
So next we have some of the strains of the algae and what is their biomass productivity and lipid productivity. So if we so if we see diatoms, There are two strains given, and the biomass productivity is around first it is 0.2 for grams per liter per day, and lipid productivity is 44.8 milligrams per liter per day, and their habitat is marine. So we can see that there are some algae which belongs to fresh water and some to saline water, and they have different biomass productivity and very different lipid productivity. So next, we have lipid content in algal cell. So here lipid content in grams of lipid per 100 gram dry algae is given for different algal strain. You don't need to remember, just learn these. It is just for your knowledge about what is the algal strain and what is the yield of the lipid content. And it is a very extensive research is going on for more improvement or increasing the lipid content in algae. Next is various types of fatty acids in algal cells. So there are some of the saturated fatty acids which are given like capric, lauric, myristic, palmitic. Again, these are the fatty acids given. If questions will be on these, then as you have seen in assignment questions, you will given the formula for these fatty acids, and you have to then proceed from that. No need to remember the formulas also. Next, we can have unsaturated fatty acids. Unsaturated are the one which have double bond in their chain. So some of the unsaturated are myristotelic and others. These are also the unsaturated fatty acid. Next, we have algal lipid and bio oil quality. So as we know, CT number, we have this learned about CT number in the last week's sessions. If the oil or fuel is high CT number, then it burns very easily. Its combustibility is very high. So we can see that the saturated fatty acids have comparatively higher cetane number as compared to the unsaturated one. And as the number of carbons is increasing, and we can see for the top one that the number of carbon is 22, and there is one unsaturated bond, and its cetane number is also comparative compared to the saturated one. Next is monitoring of favorable fatty acid lipid content in algal cell. So here is a graph between composition of fatty acid and by weight percentage and fatty acid. So we have two scenarios. A is for autotrophic and H depends heterotropic. We know that algae are autotrophic, but if the conditions are very unfavorable, then algae can also grow in heterotrophic conditions. So we can see that during the autotrophic conditions, the composition of fatty acids are very high. When the fatty acids are unsaturated, and as the fatty acids are getting saturated, then their composition are varying along with the various conditions, whether it is autotrophic or heterotropic. Next, some of the strategies to enhance the lipid accumulation in microalgae are, there are two approaches. First is the physicochemical method, and next is the molecular strategy. In physicochemical method is first is nutrient stress. So if there will be nutrient stress, then the conditions for algae will be very adverse, and in that condition algae will not try to accumulate the organic carbons in their body. Rather they will use it and go through some other routes and produce lipid and other things which is required for their survival. Next is optimization of culture conditions. So there are, for every strain there are some optimum temperature and other conditions which if we apply the conditions and optimize that, then algae or any other strain of microorganism will have highest yield. So we can optimize the conditions for algae. We can optimize light intensity or light duration. We can optimize temperature. We can optimize the salinity and etc. Next is combined stress. Like we can give multiple nutrient stress along with different culture conditions. Next is co-culturing with bacteria and fungi. And next is use of hormones, microtoxic growth condition, mixotropic growth conditions, which is used of different carbon substrate. We can use different inorganic carbon substrate for the algae to grow. Next, some of the molecular strategies are gene silencing, RNAi technology, transformation of microalgae cell, or overexpression of genes directly linked to lipid and others. So we'll move forward. So here is a picture. First, algae are cultivated. It can be cultivated in a glass flask or any other. Next, we have obtained the wet biomass. We have removed the water and we have accumulated the microalgae. But this algae has water, so we need to dry out the algae. For that, we dry the algae for 24 hours at nearly 60 degrees centigrade. Next, it is ultrasonicated by adding chloroform. These are the modifications which are done to extract lipid and bio-oil. Next, the phases after ultrasonication phases are separated. Like we will have at the top we will have the algal oil, and at the bottom we will have algae. So, and at the top we have the liquid, which is further modified. Vacuum evaporation is done for separating chloroform and algal oil. And finally, we have got the algal oil after separation from chloroform. And this algal oil can further be modified to produce biodiesel by transesterification. Next, we have cultivation or growth of microalgae as an important step for algae to oil. So we can get the biomass productivity. Suppose X is the dry cell weight and X2 is the dry cell weight at any time T2 and X1 is the dry cell weight at time T1. So we will get the biomass productivity as difference of X2 and X1 divided by T2 and T1. And we can get the lipid content as weight of the extracted lipid to the dry algae biomass. And also we can get lipid productivity as biomass productivity and lipid content in percentage. So here we can find there's a procedure given to find the lipid content. It is the Blick-Dyer method which was used to extract lipid. So 1 gram of dried algal biomass is mixed with 1 ml of chloroform and 2 ml of methanol and then kept for 18 hours at 25 degrees centigrade. So after 18 hours, the mixture is shaken tightly and again 1 ml of chloroform is added and again the mixture is shaken vigorously for 1 minute. Then to this mixture 1 ml of distilled water is added and mixed in a whirlpool again for 2 minutes. And then we will have the separation of layer and we will determine the lipid. So we'll move to the next module. So we in this module we will discuss about the reactor system for cultivation or growth of microalgae, followed by harvesting of algal biomass and then treatment of wastewater using microalgae. So first we have reactor system for cultivation or growth of microalgae. So we can grow microalgae both in open system or in closed system. But since microalgae are autotrophic, so photons or light is required. So we call the reactors as photobioreactors. Bio because biological organism like algae are grown, and photo because of the requirement of sunlight. So we can have both types of reactor. We can have open system or we can have closed system photobioreactors. So here the first picture is for this one is for the open system where there is a pond like system and algae is grown, and generally algae floats at the top of the surface and from the top it is harvested. So major types of closed photobioreactor it can be a vertical tubular or it can be a horizontal tubular. It can be a plate arrangement or it can be a plastic bag system. So next is closed photobioreactors. So it is a horizontal tubular system in which this blue one is where the fresh media required for algae is applied. So and then this this media is applied to this tubular arrangement where microalgae are growing, and then finally from these the microalgae are harvested, and these tubulars need to be subjected to sunlight for the growth of microalgae. Next, we have the vertical system where the flow is from either from top to bottom or bottom to top, and these vertical columns microalgae can be grown. Then on the right, we have a picture showing flat panel photobioreactors in which microalgae can be grown. And next, here is the comparison of open and closed photobioreactors. So since the conditions are different for open and closed photobioreactors, so we will get different results from these. So if we see, so first we will see what are the parameters required and what is the results from these parameters. So first we see, if we see the required space, and obviously for open ponds, the space requirement will be very high. And for closed photobioreactor, it is very low because we can grow the algae in columns, so the space requirement is not that much. Next is water loss. Because in open system, evaporation can take place, so there will be very high amount of water loss, and it may also cause salt precipitation. But in closed system, it is more controlled, so there won't be any evaporation, and so water loss will be very low. Next is CO2 loss. We can have very high CO2 loss from the open system because because the pond maybe is open to the atmosphere, and there, as we know, there is exchange of gases between atmosphere and water. So because of that, there may be carbon dioxide loss depending upon the pH in the pond. Next is in closed photobioreactor, since we have the closed system, so for CO2 loss will be very low as compared to the open ponds. Next is oxygen concentration. So since algae does not require oxygen, rather it is giving oxygen through Calvin cycle and through the photosynthesis. So in open system, what happens, since the pond is open to the atmosphere and there is exchange of gases taking place, so if there is high amount, if the oxygen in the open ponds is above the saturation level, then that oxygen will escape into the atmosphere, and we will have a low concentration of oxygen in the open system. But in closed system, algae is producing oxygen, so we need some arrangement to remove that oxygen from the system. Otherwise it will inhibit the growth of algae. So this is written that usually high enough oxygen in the pond system is low enough because of continuous spontaneous outgas exchange of gases taking place. And in closed system, it requires some gas exchange devices. Otherwise, it will inhibit the photosynthesis or it will give photooxidative damage. Next is temperature. So in open system, it is very difficult to control the temperature, but we can control the temperature by limiting the depth of the pond, because deep ponds have temperature differences between the surface and the bottom, and if you're going for shallow ponds, then the temperature difference will be less. But for closed photobioreactors, we need some cooling arrangements to bring the temperature in the range. Next is shear. In open system, low or gentle mixing is done, but in closed photobioreactor, fast and turbulent flow required for good mixing, because we need to mix the microalgae with the nutrient feed we are providing. So there is lot of shear. There can be lot of shear in the closed photobioreactor due to vigorous mixing or pumping. Next, we have cleaning. In open system, we do not have any issue with the cleaning. We can clean it very easily. But in closed system, we required some sort of cleaning because the algae are very sticky. They can stick to the walls, and they can grow on the wall. So because of this, the water in which algae is growing, which will become very dense, and since it can grow on the walls, so it will inhibit the transmittance of light intensity through the columns. So we need to do some cleaning in the closed system. Next is contamination risk. Since the open ponds are open, so it will have very high risk of contamination because of some other foreign species. But in closed system, the contamination risk is low because the system is closed. So the foreign species cannot come into the closed photobioreactor. Next is biomass quality. So since in the open system, we do not have that much controlling. So the biomass quality may be variable in the open system, but in for the closed system, we can control the condition very well. So the algae produced will be of very high quality, and whatever properties we want from the algae, that can be produced in the closed photobioreactors. Next is biomass concentration. um, Again, since the open system, we cannot control that much, so it has low biomass concentration. But in closed system, the biomass concentration is high. It is between 2 to 8 grams per liter as compared to 0.1 to 0.5 grams per liter in open system. Next is production flexibility. Only few species possible, and it is very difficult to switch from one species to other in the open ponds. But in closed photobioreactor, we can grow um, any species or large number of species we required, and switching is also possible due to controlling conditions. Next is process quality and reproducibility. So we have limited flow speed or mixing in open ponds, but in closed photobioreactor we can go to turbulent mixing and other conditions, but up to a certain tolerance limit, because there may be possibility that a very high mixing and turbulence can inhibit the algae, or it can also lead to loss of or dying of the algae. Next is the comparison of various types of closed photobioreactor. So we can have tubular photobioreactor, or we can have column photobioreactor, or flat panel photobioreactor. So biomass yield is very high in tubular photobioreactor as compared to column and flat photobioreactor. Next is exposed surface area for light. Since we are using tubular, so it will have very high area exposed to light. And next is manufacturing cost is very high for flat panel, and it is less for tubular. Next is problem due to oxygen and carbon dioxide accumulation. So it will have very high problem in tubular and flat panel photobioreactors, and it will have less in column photobioreactors. Next is scale up possibility. So the tubular photobioreactors can be scaled to commercial level very easily as compared to other. And for these, the maintenance cost is also high as compared to other two. Next is the dimensions of various type of photobioreactors. So these are some of the values. So for open pond, typical dimension of depth is between 1 to 15 centimeter. And for horizontal tubular photobioreactor, inner dia of the tube is around 2.5 centimeter. And for vertical column photobioreactor, the inner dia is 2.6 centimeter. And for flat panel photobioreactor, the width is around 3.2 centimeters. So these are for the lab scale taken from research paper. So these are the lab scale reactors. Next is harvesting of algal biomass. Now we have grown the algae in some of the reactors. Now we need to harvest the algae. And since these are microalgae, so we need some harvesting technique to accumulate these algae and then extract from the system. So first we have the microalgae suspension. Then we will do the bulk harvesting, in which water is removed, and by using sedimentation, flocculation or flotation, we will increase the solid content, or we can say that we have increased the percentage of algae and we have removed the water. And then we are drying. um, we have the concentrated biomass in which have 2 to 7% dry weight, and then thickening is done, in which rest of the water is removed and we are getting the algae culture. It can be either done by ultrasonic agitation, or we can done by centrifugation, or it can be done by filtration. So the unit operations used for algae harvesting is, first is flocculation. So what is flocculation is that it is the aggregation or accumulation of the microalgae cell to increase its effective particle size, so that due to increase in its particle size it can settle and then it can be removed. So but in case of algae, cell wall is one of the barrier to facilitate the extraction, and thickness of cell wall is also affected by the conditions of the cell wall at the time of harvesting. So we need some source of flocculants to bioaccumulate to accumulate the algae. So we can use alum or ferric chloride. These are the inorganic salts, or also known, or we can call them chemical flocculants. We can use them to harvest algae. But this method is often too expensive because of the cost associated with these chemicals. So also in interrupting carbon dioxide supply to algae system can cause microalgae to flocculate in its own. It is called autoflocculation. So what we can do is we can interrupt the carbon dioxide supply to the system, and because of this algae may start dying, and it can stick to one another, and the process is known as autoflocculation. Next we have the mechanism of flocculation. Flocculation is a process wherein colloids come out of a suspension in the form of flock or flake. We can do the flocculation either by just gently mixing it, or we need to add some external chemical for the flocculation to take place. So generally flocculation takes place by two mechanisms. First is perikinetic flocculation. In this flocculation, what happens? Particles stick to each other due to the Brownian motion or random motion of individual particle. Next is orthokinetic flocculation. This flocculation takes place due to collision between the colloidal particles taking place, and this collisions takes place due to by applying external energy, such as by applying steering in the system. Next is flocculants promote flocculation by causing colloids and other suspended particle in the liquid to aggregate, forming a floc. So what happens? Flocculates are it may be some organic or inorganic chemicals which we add in the system, and due to this the suspended particle content in the system increases, and there is collision taking place between the colloids and these chemicals, and because of that there is a formation of flocks, and which can be further extracted. Also, we can use, since we also use flocculation, there are different mechanisms of flocculation. We can flocculate by charge neutralization, or we can flocculate by just by bridging. It depends on what is the compound is to be flocculated. Next is, many flocculants are multivalent cations such as alum, iron, calcium or magnesium. These are the positively charged molecules. So these can be used to these can be used to accumulate the negatively charged particles because of the charge neutralization. So as we know, colloids are the particles which cannot settle which cannot settle by gravity, or it requires very long time for settling, because these colloid particles are repelled by each other due to the charge. And generally these colloid particles, if we see in the water system, are negatively charged. So to neutralize these charge, we add the positively charged molecules like aluminium or calcium salts, and these cations neutralize the charges, and since the charge is neutralized, so the colloidal particles come closer to each other, they aggregate, accumulate, and flocks are formed, and which can further be removed by either sedimentation or filtration. So since we are adding the chemicals, and these species, or these like aluminium, iron, calcium, it can form number of species and depending upon the pH. So it can form different hydroxide or carbonate species depending upon what is the pH and what is the salinity, ionic strength, and it can also form some of the insoluble hydroxides. So if the insoluble hydroxides are formed, which precipitates and linked together to form long chain or meshes, and which these meshes can physically trap the small particles and they can form larger flocks. So apart from these inorganic salts, we can also use some polymers or organic polymers like long chain polymers. Polyacrylamide is very extensively used in algal accumulation, or it is also used to prevent soil erosion. So it can this polyacrylamide modified polyacrylamide can be used as a flocculant to accumulate the or flocculate the microalgae. Next, we have flotation. So usually flotation is used in combination with flocculation. In flocculation, we have formed the flocks. So we can float these flocks to at the surface, and then we can extract these flocks, and we can get the microalgae. So flotation is followed by flocculation, in which the flocks are made to float on the surface media, and then they are removed. Next is sedimentation. So in sedimentation, after flocculation, gravity sedimentation is done to settle the large algal flocks which are made in the flocculation step, and then these algae can be removed. So in gravity sedimentation, we get 1 to 5% solid algae biomass harvesting. So since in this sedimentation gravity settling is used, so sedimentation of algae are influenced by the settling velocity of the microalgae. And the settling velocity is proportional to the cell dimension. So we can increase the settling velocity by increasing the cell dimension. Next we have centrifugation. So in centrifugation, it is a method of separation of algae by using a centrifuge to it into the bottom of the tank. So this centrifugation can be very helpful on commercial and industrial scale, but it is very expensive for personal use or at small scale. But very in centrifugation, very high forces are used for centrifugation, which can damage some of the sensitive algal cell. Next is ultrasonic agitation. So ultrasonic field concentrate the cell due to acoustic forces, but the final separation here is also based on gravity forces. Next is filtration. We can do the filtration by using some membranes of modified cellulose with the help of a suction pump. So the greatest advantage of filtration is that it is able to collect microalgae cell with very low density. But there is some limitation of filtration, is that concentration by filtration is limited to small volume and with eventual clogging in the filters, and because the microalgae are being filtered, so they clog the pores in the filters. So this is the limitation of filtration. So filtration is best suited for large microalgae, normally greater than 70 micron. Next, we have some techniques used for harvesting microalgae. So the first strain is Spirulina platanus. So for this, we use vacuum filtration. And the condition is that vacuum filtration is equipped with regenerated cellulose membrane. After filtration, we can regenerate the cellulose membrane, and the pore size of the membranes is 4.45 micron. So here these are the different species of the microalgae and different methods and the conditions which are applied for their harvesting. So here is the comparison of some microalgae harvesting technique. So if we are taking the gravity sedimentation, then we are settling the algae by gravity. So relative cost is low, and yield is taken as total suspended solid in percentage. So we are getting 1.5% algae, and the energy usage is also very low. It is around zero point 0.1 kilowatt hour per meter cube. But this technique is not very efficient for rapid biomass recovery, because we need to provide some time, some minimum time for the microalgae to settle at the bottom of the reactor. Next is inorganic chemical flocculation. Since we are adding chemicals externally, so there will be very high cost associated with these chemicals, but the yield is very high. Here it is around 90%, and energy usage is not that much. It is around 0.33 kilowatt hour per meter cube. So, but since we are using salt, and the complexation of these salts are pH dependent, so the efficiency of the method will also very much depend upon the pH of the media. Next is polyelectrolyte flocculation. These are some of the organic polymers which we use, like polyacrylamide. So here also we are requiring some chemicals, so the cost will be very high for the chemicals, but and the yield is around 15%, and also energy usage is high. It is 14 to 81%. Here also there will be some pH dependence of the polymers, but lesser than the inorganic chemicals. Next is centrifugation. Here we need to centrifuge the water, so relative cost in cost will be very high, and we are getting around 22% yield with 8% of energy, 8 kilowatt kilowatt hour per meter cube of energy requirement. These the remark is here is that it is cost and energy intensive, but it is very suitable for at a high or commercialized level. Next is filtration. We can do filtration at the normal natural pressure, or we can do at pressurized pressure. The cost associated with filtration is high, and the yield can be around 6% or 22%. And next is flotation. Here also the cost is very high. And next is autoflocculation. Since the algae are flocculating on their own, so there is no cost associated with this. So these autoflocculation can happen in absence of carbon dioxide. Next, here is the example of wastewater treatment using algae. So first we can see that here is the municipal wastewater sewage. So here the algal strain uses cholera, SP. The nutrient removal for nitrogen is very high, it is 89.9%, and for phosphorus it is 80.9%, and for COD it is 90.3%. And some of the process condition is that initial nitrogen nitrogen, phosphorus and COD was 132.3 ppm, 215 ppm, and 2390 ppm. So the temperature used here was around 25 degrees centigrade, and light intensity was is also given, and this was done in batch for 14 days. Next is municipal wastewater. It is feed as raw without any autoclaving. Here the nitrogen, phosphorus and COD removal is nitrogen is 89.1%, 80.9% phosphorus removal, and 90.3% COD removal. Next is soya bean processing wastewater. Here the nitrogen removal is 89.9%, phosphorus is 74.5%, and COD is 84% by C. pyrenoidosa algal strain. Next is piggery wastewater. Here also nitrogen removal is 89.1%, phosphorus 80.9%, and COD 90.3%. So we'll move to module 4. So module 4 was on energy production from algal bios. So we can make biodiesel or biofuel from Algal biomass. So the contents for this module is biodiesel as an important option for energy production from algal biomass, bio-oil production from algal biomass, conversion of bio-oil to biodiesel, types of conversion process, mechanism and comparison, factors affecting biodiesel yield. So here is a picture showing important energy production route for algal biomass. So from algal biomass we can produce bio or biodiesel, biojet fuel, or we can produce syngas, biogas, pyro oil. So here we will discuss about biodiesel and biojet fuel. So for production of biodiesel or biojet fuel, first algal biomass is taken and oil extraction is done, and this bio oil is upgraded and by transesterification to produce biodiesel or biojet fuel. Next, here is a picture chart showing how biodiesel or biodiesel extracted from algal biomass. So first, harvested microalgae is dried, and then the dried algal biomass oil extraction is done by using some solvent, and then separation of oil, separation of biomass and separation of bio oil plus solvent is done, and finally the solvent is extracted, separated, and we get the bio oil. Next is the mechanism of oil extraction using solvent. Some solvent is used, and depending upon the polarity, these solvent go and interact with the lipids, and depending upon the charges, these lipids are extracted in the solvent, in the liquid phase. Next, we can here is the some of the organic solvents which are used to extract different microalgae species. So we can use salt, methylene chloride, methanol, or chloroform, methanol, hexane, isopropanol. These are the solvents which are used for extraction of algal lipid. Next, we have mechanism of supercritical CO2 extraction. Here is A is the mixture of microalgae biomass and diatoms. So supercritical CO2 is used, and it interacts with the algal biomass and takes out the lipids from the algal biomass. Next, here are some of the studies on extraction of microalgal lipid by supercritical carbon dioxide. So you just go through these. So here is the single step oil extraction. So we are drying the algae. After extraction of algae, after harvesting of algae, there is lot of moisture or water in the algae. So we need to dry it, and for drying we need more than 100 degrees centigrade temperature. It is around 100 to 105 degrees centigrade, and for that high temperature, lot of energy is required, and for energy cost is associated. So when lots of capital is required for drying of the algae. So here a single step oil extraction is shown, where the matured algal biomass are passed through a pipe where some low voltage power is applied, and because of this voltage in the algae, the lipid and the biomass are separate. Our lipid is released from the algal biomass, and in the extraction tank we have the algal biomass along with the lipid, and finally these are sent to a separator, gravity settler, where the lipid, water and biomass are separated depending on its density, and we extract the lipid, and we can recycle the water after treatment, or we can return it to the bioreactor, and we can get the biomass out of this. Next is biodiesel production route through algal biomass. So we have the algal biomass. First oil extraction is done. Then this oil is converted to biodiesel by transesterification. And we know in transesterification we need some catalyst. It can be alkaline, acidic or enzymatic catalyst, and we need some solvent. And finally the biodiesel, or we do filtration or distillation, and finally we get the biodiesel. Here is the mechanism for transesterification. I will request you all to go through these in the slides. Next is the different methods for biodiesel production. So these are the methods: catalyzed transesterification process or oscillatory flow reactors. You just go through these in the slides. Here's the mechanism. Please go through these. So the factors affecting biodiesel yield. So factors which affect the biodiesel yield is oil temperature, reaction temperature, ratio of alcohol to oil, what is the catalyst type and its concentration, intensity of mixing, and purity of the reaction. Next is comparison among base, acid, and enzyme catalyst esterification reaction. So in transesterification, we can use base catalyst or acid or enzyme catalyst, and we have, if we are using the base catalyst, then reaction time is very high in base catalyst as compared to acid, and reaction rate is very high in base catalyst as compared to acid and enzyme catalyst. And also we have different characteristic effect of free fatty acid and oil. In base catalyst it is high. Next is cost of the catalyst. Enzyme catalyst are very high. Cost of enzyme catalyst are very high as compared to base and acid catalyst. Next, for base catalyst we use NaOH or KOH, and for acid catalyst we use sulfuric acid or hydrochloric acid. For enzyme catalyst, we use lipozyme IM60 or novozyme 34435. Next is deactivation of chances of deactivation of catalyst. So base catalysts are very susceptible to deactivation, followed by acid catalyst and enzyme catalyst. Next is possibility of catalyst recovery. Enzyme catalyst can be recovered very efficiently as compared to base catalyst. Next is problems in product recovery. It is very high in base catalyst, and we also get byproduct in base catalyst, that is glycerol. And next is effect of alcohol uses. It is high in enzyme catalyst. Comparison of different types of trans-esterification process. So if we are using catalyzed trans-esterification, then it has certain advantages and disadvantages. The advantage is it is primitive and mostly used process. The disadvantage is that the performance is very highly affected upon with the what type of catalyst we are using. So we can use various types of catalysts. We can use homogeneous, heterogeneous, or biocatalyst can be used. So the other process which can be used is catalyzed transesterification using co-solvent. So the disadvantage is that the co-solvent are volatile and are not environment friendly. It causes air pollution. And the solvent separation also increases the cost associated with the production of the biodiesel. And the advantage is that improved solubility and high mass transfer rate between oil, solvent, and catalyst. Then comparison of different types of trans-esterification process. Next process is oscillatory flow reactor assisted catalyzed transesterification. In this, there is improved heat and mass transfer between medium, but this technology is very recent and it is under extensive research. It is not well proven. Next is microwave technology assisted catalyzed transesterification. Here the energy requirement is less, but scale up to commercial scale is difficult. Next is ultrasonic technology assisted catalyzed transesterification. There is improved mass transfer rate between media, but this is also a new technology. It is not well proven. So I'll move to the last module. So in this module, we will discuss about upgradation of algal oil to biodiesel using homogeneous and heterogeneous catalyst, followed by quality parameters of algal oil, algal biodiesel and its stability, challenges for microalgae and integrated scheme for utilization, then what are the biojet fuels, and what is the research status on algae to oil. So here is the upgradation of algal oil to biodiesel. So here some of the microalgae species are given, and the oil extraction method used for that algae, what is the catalyst used, and what lipid content we get, and what is the biodiesel conversion rate. So these are taken from different papers. You just go through these, and these are for your references. There is no need to no need to remember these. So next is heterogeneous catalyst and trans-esterification of bio-oil. So we can use different catalysts. So for first, the solvent uses methanol and catalyst uses calcium oxide supported in aluminium oxide. Here the temperature is kept 50 degrees centigrade, and here the yield can be 23 or 97.5%. So next is methanol. Solvent is methanol and catalyst is magnesium oxide supported in aluminium oxide. Here temperature is 50 degrees centigrade and alcohol to oil ratio is 6:1. Here the catalyst loading is 2% by weight and retention time is 4 hours and yield is 16%. And next is the solvent uses methanol, methylene dichloride in 3:1 ratio by volume. And here the catalyst uses magnesium zirconium solid base catalyst. And we are getting the yield here is 28%. Next is now comparison between heterogeneous and homogeneous catalyzed transesterification. So if we are using homogeneous catalyst, then the reaction rate is fast and all, and the conversion is fast and high conversion in homogeneous catalyst. But in heterogeneous catalyst, the conversion rate is moderate. Next, for homogeneous catalyst, these are homogeneous as same phase as the other components. So these catalysts cannot be recovered, but it need to be neutralized, leading to the waste chemical production. But the heterogeneous catalyst has different phase than what is being reacted, so it can be removed from the system. Next is processing methodology. So we have limited use of continuous methodology in homogeneous catalyst, but in heterogeneous catalyst, continuous fixed bed operation is possible. Next is presence of water or free fatty acid. Homogeneous catalysts are very sensitive to presence of free fatty acid because formation of soaps takes place. But heterogeneous catalysts are not sensitive to free fatty acid. Next is catalyst reuse is not possible in homogeneous catalysts, but it is possible in heterogeneous catalysis. Next is cost. Homogeneous catalysis is costlier as compared to the heterogeneous catalysis. Next, here is the different quality of biodiesel we get. So first we see the properties density. So the biodiesel from algal oil has density of 0.864 kilograms per liter, and diesel oil has 0.838 kilograms per liter, and ASTM standard biodiesel has 0.84 to 0.9. So we can see that almost all the parameters are near to the standards of the ASTM biodiesel standard, and only the flash point of biodiesel from algal oil is 155 degrees centigrade, but for STM the requirement is minimum 100. So it is so the biodiesel from algal oil are meets all the ASTM biodiesel standards, and they are very good source of diesel fuel for the vehicles. Next is stability of biodiesel. So the biodiesel are very susceptible to the oxidation because with oxygen different reactions takes place, and these lead to the degradation of the biodiesel. So the stability of biodiesel is divided into oxidation stability, thermal stability and storage stability. So we have first oxidation stability. So oxidation of biodiesel takes place by oxygen due to the presence of double bonds on the fatty acid chain. So these double bonds are oxidized by oxygen and the degradation of biodiesel takes place. Next is secondary oxidation. Once the fatty oil hydroxy, so you once sorry, we'll go through this. So the double bond often offer high level of reactivity of oxygen, especially when it is placed in contact with air or water. So first what happens, the initiator is a free radical. Free radical is formed. This is produced by decomposition of hydroperoxide that is present in the fat, and due to high temperature of metal ions in the lipid environment helps in its formation. What happens, radical is formed, and this radical reacts with oxygen and form ROO radical, and this ROO radical further reacts and form acid along with R radical. And finally, termination reaction take place, and in which two R radicals react to form RR bond, and the ROO radical which are formed, these reacts and form stable product. And what happens, a free radical, these attack the lipid, and these leads to formation of allylic radical, and these leads to degradation. Next is secondary oxidation. Once the fatty oil hydroperoxides are formed, they ultimately decompose to form aldehydes. And as hydroperoxide decomposes, oxidative linking of fatty acid chain can occur to form species with high molecular weight. So oxidative polymerization is taking place, and with increase in polyunsaturated fatty acid chain, it enhances the oxidative polymerization in the fatty acid, resulting in the formation of insolubles. Next is the method to increase the stability. We can use antioxidants as additive. These can be natural or synthetic antioxidants, and these react and form ROOH along with the A stable product, and these leads to increase in stability. Next is challenges for microalgae. So one of the biggest challenges in culturing microalgae for biodiesel is to find a suitable strain that grow fast and capable to produce as much lipid as possible during its culture. So it is very difficult to find out a particular strain of microalgae which can be grown very fastly, and it can be used for maximizing the lipid content in its culture. Another major challenge is to design a cost-effective photobioreactor, because and also which mitigates the contamination risk, because if we are using open system, then there is chances of contamination of the photobioreactors, algal culture in the photobioreactor. Next is there is a large cost associated with the oil extraction from microalgae, and apart from these challenges, biodiesel from microalgae is the only renewable biofuel that can substitute petrodiesel completely, because the quality of biodiesel we get here is very high, and these can be used to substitute the petrodiesel. Another advantage of microalgae is that it is using inorganic carbon CO2 as their carbon source, and this can use to reduce the greenhouse gas effect. So here is a scheme for algal biomass utilization. So here we have wastewater coming, and we have grown the algal cultivation, we have grown the algal culture, and this algal culture can be used to produce biomass or biodiesel, or the wastewater reject or CO2 can be fed to produce in under in sorry anaerobic conditions to produce the biogas, and then we will get the we will get the compost out of this biogas and along with the biogas. So next is biojet fuel. So we have two types of biojet fuel. First is used in civil or commercial jet fuel, or other is the military jet fuel. So there are four types of civil or commercial jet fuel. and three types of military or military jet fuel, type 1, type 2, and type 3. You just go through these in the slides. Here is the biojet fuel routes. We can use the algal biomass to produce bio-oil through trans-esterification, and we can also go through other route that after algal biomass it is pyrolyzed, bioleum is produced, and it is further upgraded to produce the biojet fuel. Next, here are some of the exam institutes which are focusing on research in the field of algal fuel. You just go through these in the slides. So I think this is the last one. So we'll move to the assignment questions. So we will just now discuss the previous year question based on week 8 module. So the first question is, which of the following algae harvesting technique has highest total suspended solid yield? A. Flotation, B. Sanctification, C. Polyelectrolyte flocculation, or D. Inorganic chemical flocculation. So I will give you guys 2 minutes. Just take your time and write your answers in the chat box, and then we will move to the next question. So till now I haven't got any answer. So I request everyone to please participate and write your answers in the chat box. So we will see what is the solution for this question. So I got one answer by Gaurav. It is flotation. No, the answer is wrong. Flotation is not the correct answer. So I'll give you one more minute. So just take your time, think, and write the answer in chat box so that I can see. So I got only one answer and we have 4 participants. So I got one answer C. So C is the correct. No, C is not the correct answer. So we'll see the correct answer. D is the correct answer, that inorganic chemical flocculation has the highest total suspended solid yield. Next is the compounds A and B in the following trans-esterification reaction are. So we have the reaction triglycerides with alcohol give A and B. We have to identify what is A and B. A is either aldehyde or B is acetic acid, ether or glycerol, esters and glycerol, esters and acetic acid. So I'll give you 2 minutes. I request everyone to please participate and write your answer, because day after tomorrow you have exams, so it will be a revision for you all. So just write your answer. I got one answer. See, I need one more answer, then we will proceed to the next question. C, the correct answer is C. Triglyceride with alcohol give esters and glycerol. So next question is, the order of reaction rate for esterification reaction is A, base catalyzed followed by enzyme catalyzed and then acid catalyzed, or B, base catalyzed then acid catalyzed then enzyme catalyzed, or C, enzyme catalyzed then acid catalyzed and then base catalyzed, or D, enzyme catalyzed then base catalyzed and then acid catalyzed. So we have to say the order of reaction rate for esterification reaction. So I'll give you 2 minutes. So please write your answer in the chat box. So I got 3D and 1B. So let's see which is the correct option. So B is the correct option. Base catalyzed esterification reaction has the highest reaction rate, followed by acid catalyzed and then enzyme catalyzed. So the next question is, the operation E in bio oil production from algal biomass is. So here is a chart which shows the bio oil production from algal biomass. We have to say which is the which process is A. It is either extraction, distillation, evaporation, or filtration. So similarly, I'll give you 2 minutes. Please write your answer in the chat box. So let's see which is the correct option. I got 5 answers as A. So A is the correct option, that uh, from dry algal biomass extraction is done, from extraction of bio-oil is done. Next question is, this is a numerical and this is a common data question for question 5 and 6. So the numerical is, bio-oil extracted from a oil seed sample has 85% glyceride containing 3 long chain which can produce methyl esters of lauric acid, myristic acid and palmitic acid in equal molar ratio during transesterification using methanol and NOH catalyst. Calculate the amount of biodiesel produced by transesterification of 8 kg of bio-oil. Assume efficiency of conversion is 75% and 12% of palmitic acid is converted to soap. How much glycerol will be produced? So we have to find out the amount of biodiesel produced along with how much glycerol is produced. So I'll give you guys 5 minutes. Just try to solve this question and write the, so I have not given the option. So and just solve it and write the option which you are getting. So here these values 4, 6, first value is for the bio oil production and the second one is for glycerol. So please solve it. I'll give you 5 minutes. Yes, Manimaran, I will explain how to solve this problem. So first try to solve it. So just wait for others. We will wait for others to solve it. Then I'll explain you how to approach this problem. So I got one answer. So I'll wait for 2 more minutes for everyone to at least try solving this question. So I got only one answer. Now let's see how to solve this. So correct answer is C. We have been given that the bio oil consists of 85% glyceride, and we have given the three acids lauric, myristic, and palmitic acid, and these will be converted to esters of its acid. So these three are present in equimolar ratio, and we are here during transesterification. Methanol is used and NOH is the catalyst. So since we have given the formula for these acids, lauric, myristic, and palmitic acid, so we can find out the formula for the methyl esters from these acids. So basically the ester and acid of these have the same uh, chemical form, same formula, but their arrangement is different. So we will find out the methyl ester from these. Next, we will write the formula of the oil. So uh, So lauric, myristic, and palmitic acid will give us this this algal oil, and this algal oil is reacted with methanol in presence of NOH to produce glycerol and biodiesel product. So this is the transesterification step. So we have the triglyceride. We will find out what is the molecular weight of triglyceride. So this is the triglyceride. So we will find out the molecular formula. So we will calculate how many numbers of carbon are there in. So we have 45 carbon, 86 number of moles of hydrogen, and 6 oxygen. So we'll find out the molecular weight of triglyceride. And this is the formula for glycerol. We will find out the molecular weight of glycerol. It has 3 carbon, 8 hydrogen and 3 oxygen. So molecular weight of glycerol is 92 grams and of triglyceride is 722 grams. Next, we will find out the molecular weight of these acids which have been given in question. So these have molecular weight of 214, 242 and 270. So these acids and their esters will have the same molecular weight. Next, we have been given that 8 kg of we have been given that 8 kg of bio oil is transesterified. So the basis is 8 kg of bio oil, and out of this 8 kg 85% is triglyceride. So triglyceride will be 0.85 into 8, that is 6.8 kg, and moles of triglyceride is 6.8 divided by molar mass of the triglyceride, which we were getting 722. So the moles of triglyceride is 6.8 upon 0.722, that is 9.418 kilomoles. Next, we have 75% conversion of triglyceride. So moles of triglyceride converted will be 0.75 into 9.418, that will be 7.0635 kilomoles. And as per the transesterification reaction, 1 mole of triglyceride is reacting with 1 mole of methanol to produce 1 mole of glycerol and 1 mole of 1 mole of bio oil. So we will have glycerine or glycerol production will be 7.0635 moles into the molar mass of glycerol, that is 92 grams, and it will be 0.6498 kg of glycerol. And now we have to find out the amount of bio oil produced. So we'll find out how much a mass of each acid is produced. So mass of this is number of moles into its molecular weight. We will get 1.5116. Then for next acid it is 1.709 kg, and for last acid, palmitic acid, we have, it is given that, so in the last statement it is given that assume efficiency of conversion is 75% and 12% of palmitic acid is converted to soap. So 88% is converting to biodiesel and rest is converting to soap. So here the palmitic acid converting to biodiesel is 88%. So it will be 7.0635 into its molecular weight into 88% will give us 1.678 kg. So overall the mass of biodiesel produced will be this 4.8986 kg. So the correct option is C. So we will move to the next question. The data to be used for this question, we need the data from the question 5. So the question is, in the question 5, how much soap will be produced? So I will give you I will open question 5. So from this question, we have to find out how much soap will be produced. So I'll give you 5 minutes for this question also. Just try to solve it and then just write your option, just write your numerical value in the chat box, and then we will see how to approach this question. So I got one answer as 0.235 kg of soap produced. Let's see. So correct option is C, 0.2356 kg of soap will be produced. So the mass of palmitic acid produced is 7.0635 into 0.214. So these are the mass of the lauric, palmitic, and other acid produced. So this acid is used for soap formation. So around 12% soap is produced. So the amount of this acid used for soap formation will is 0.2288 kg. Now the reaction for soap formation is that this acid reacts with NOH to produce the soap. So the molar mass of this acid is 270 acid ester is 270 grams, and the molar mass of the soap produces 278 gram. So 270 gram of this is producing 278 grams of the soap. So 0.228 kg will produce 278 into 0.228 upon 270 kg of the soap, that is 0.2356 kg. So the correct option is C. So we'll move to next question. It is also a numerical question, numerical based question. So the question is 60 kg of a waste cooking oil was fully dissolved in small amount of neutralized ethanol by heating and titrated with N by 20 KOH solution using phenolphthalein indicator. If the titer value is 50 ml, determine the acid value of the oil in milligram KOH per gram of oil. So we have to find out the acid value. So again, I will give you 5 minutes for this question also. Just solve and write your answer or option in the chat box. So we will see how to solve this question. Kavita ji, please mute yourself. So, so the correct answer is A, 2.337 grams milligram QH per gram biodiesel. I got one answer as A. Let's see. So acid value is given as 56.1 Vc by m, where S is the acid value in milligrams KOH per gram of bio oil or milligram of base per gram of bio oil. C is the concentration of KOH used for titration in moles per liter. V is the volume of KOH employed for titration or volume of KOH consumed for titration. M is the mass of the sample taken to be analyzed. So here we have C as N 1 by 20, C is 1 by 20, V is 50 ml and M is 60 gram. So we will put these in the formula and we will get the acid value as 2.3375 milligram QH per gram bio oil. So correct answer is A. So next, so this question is also a numerical based question. The question says a 250 ml bio oil sample is reacted with 81 gram iodine monochloride. After reaction, Ki is added in it and the liberated iodine is titrated with sodium thiosulfate. If 0.22 moles of sodium thiosulfate is consumed to reach the titer value, determine the iodine value of the oil. So we have four options. We have to find the iodine value of oil. So I'll give you 5 minutes. Please solve this question and write your answer or option in the chat box. So we'll see how to solve this question. The correct answer is B. Iodine value is 14.16. So the excess iodine monochloride will react with sodium iodide and form iodine. So the reaction is ICl plus Ki gives KCl plus IAD, and this will be further converted to iodine as per the next reaction. That iodine will react with sodium thiosulfate and produce NaI. So from the above reaction we can see that uh, 0.22 moles of, that is 1 mole of iodine reacts with 2 mole of sodium thiosulfate. So 0.22 moles of sodium thiosulfate will react with 0.11 moles of iodine. That will be 253.8 into 0.11, that will be 27.918 grams of iodine. So next is 162.35 grams of ICl. ICl, this is 162.35 is the molecular weight of ICl. It has 126.9 grams of iodine. This is the molecular weight of iodine. So 81 gram of ICl has 81 into 126. This is unit. It can be found from unitary method into 126.9 upon 162. It will give us as 63.31 grams of iodine. So the iodine which will be used by 250 ml of oil is, we have total 63.31 grams of iodine, and this much 27.918 gram is left. So the iodine which has been consumed is 63.31 minus 27.918, that is 35.39 grams. So iodine value is found for 100 ml of the oil. So for 250 ml, so iodine consumed is this much. So for 100 ml, we will find out as 35.39 into 100 by 250. That will be 14.156. So the correct iodine value of the oil is 14.16. So the option B is correct. So we have two more questions. So the next question is, the magnitude of oxidation of biodiesel in presence of air and high temperature depends on A. Presence of saturated fatty acid, B. Presence of unsaturation in fatty acid, C. Presence of aromatic compounds, or D. Viscosity of biodiesel. So I'll give you 2 minutes. Just take your time and write your answer in the chat box. So the correct option is B, that presence of N saturation in fatty acid. Uh, this the presence of double bond leads to the oxidation of biodiesel. So the correct answer is B. So next question is the density in kilograms per liter of biodiesel according to ASTM standard should be in the range of A 0.84 to zero point 0.9, 0.74 to zero point 0.8, or 0.89 to 0.98, or 1.04 to 1.2. So again, I will give you 2 minutes. Just take your time and write your option in the chat box. So I got one answer as C. Let's see which is the correct option. So A is the correct option, that density of biodiesel as per ASTM standard should be in the range of 0.84 to zero point 0.9. So these were the questions for today. So thank you so much for joining. If anyone have any question, then please ask.
Excuse me, ma'am.
Yes.
Ma'am, what is the distribution of numerical and theory type of questions in the exam?
Sorry, I don't know about this. You can mail to NPTEL to ask about this.
Okay, I understand. Also, like, if you could guide us, like, what all things we